Most of the work on automatic detection and classification of unmanned applications over the past 20 years has been focused on ground and aerial vehicles. Recently, the research has also focused on unmanned surface and underwater vehicles for autonomous capabilities. The ability to recognize and identify obstacles becomes more essential with USVs, which stands for Unmanned Surface Vehicles, autonomous capabilities, such as obstacle avoidance, decision models, and other artificial intelligence abilities using low-cost sensors. One of the most difficult challenges for USVs navigation is the recognition of obstacles around the vehicles without human intervention. This task is known as automatic target detection. An efficient ATD system should achieve a high detection percentage for targets while maintaining a minimal false alarm rate. However, ATD algorithms are very sensitive and unstable due to clutter elements. This presentation introduces multi-target automatic algorithm stages to acquire, identify, and track targets from an unmanned surface vehicle located in marine environment with LiDAR sensor challenging clutter. We present several clutter models and formulations to handle clutter phenomena. A high-quality sensor is required for close to mid-ranges as a substantial part of the detection and alert belt of the USV. As with many other sensors, the primary limitations of LiDAR sensors in marine environments are related to clutter. The Velodyne HDL64ES2 LiDAR, the Rolls-Royce of its kind, consists of 64 pairs of laser emitters and receivers which provide us 3D range scans. Typical data in marine environments with sea clutter can be seen in the next slide. Here can be seen such clutter examples. On the upper figure, laser returns from water are rated by recent passage of small propeller-driven boat. In the lower figure, there are returns from kelp at the sea surface between 10 to 30 meters. Here is another example of clutter which emphasizes the complexity of dealing with clutter, where the color represents the intensity of the return. Therefore, it ought to be either filtered or the obstacles distinguished by an efficient algorithm using a GM-PhD filter to detect and track multiple targets. As for the first approach, which relies on modeling the clutter and filtering it, we were focused in three models. The first is a one-dimensional stochastic model, which is an extension of the classical approach. It relies on the phenomenological model of the dynamics of the sea, as can be seen in the following figure. Basically, two kinds of waves are encountered at the surface of the sea, generated by two different mechanisms: capillary waves and gravity waves. Capillary waves are generated by the influence of the wind and express the surface tension of the water, while gravity waves are mainly generated by the accumulation of gravitational forces and are the main energy carrying factor. The combined effect of capillary and gravity waves over the scattered electromagnetic waves translate into composite echo, which is the sum of two components, one having a gamma PDF corresponding to a large-scale, slow varying physical structure, and the other having a Rayleigh PDF corresponding to small-scale, rapid varying physical structure as can be seen. The advantage of this model is the compatibility with existing radar processors and detection algorithms. However, this model has been stretched to the limit. It's quite difficult to obtain a valid set of parameters for an assumed PDF from recorded sea clutter samples, leading to poor results. Moreover, it's not logical to describe the sea using only one variable. However, adding more dimensions removes simplicity. In both of the following examples, there is similarity between the real clutter and the simulated one. The third is the chaotic model, which assumes that the processes involved in sea clutter generation are non-random but purely deterministic phenomena. This approach also requires a new radar processor paradigm. Results obtained from one of the prototypes of this model seems very promising, achieving perfect detection. More real data validation and noise robustness are required for credible validation. As a result of the inefficiency and inaccuracy of all the models above, there is a need for a complete different approach: tracking. The objective of the multi-object tracker is estimating the state of an unknown number of objects based on the measurements of the object corrupted by noise in the presence of clutter. And so, here is the object tracker model. The sensor gives us three values: azimuth, distance, and intensity. Considering the calibration values, the pilot coordinates are calculated and toward the right values of the angles and the distance. The range image is segmented using the mean-shift segmentation technique. It consists of two steps: filtering, is known as discontinuity preserving smoothing, followed by clustering. Descent rates of the cluster are then delivered to the tracker as a measurement set. We can see in this illustration an intuitive explanation. Given region of interest, which is defined by the bandwidth, we search for modes, which are the local maxima points, by calculating center of mass of the region. Then we move to the center of mass by the normal and direction of the mean shift vector, and then we calculate again and again until the normal is 0, which is equivalent to derivative of 0. Here are some results of this algorithm. It can be seen in both of the following cases that the images are smoothed by using mean shift filtering. In the following figures, the horizontal axis represents the azimuth, and the elevation is represented by the vertical axis. The value of each pixel represents the distance. Figure A is the given range image which was acquired by the LiDAR. Figure B is mean shift filtered, while figure C is the segmentation result. As can be seen, the clutter is slightly filtered and should be completely ignored in the following stage, which is the tracker.